Third method is called Havel-Hakimi result. So what is the importance of Havel-Hakimi result? Suppose if they provide a huge length of degree sequence, then it is not possible to draw the graph, right? Can you plot the graph? No. In such case, we can take help of Havel-Hakimi results. Okay. What is the meaning of Havel-Hakimi results? Havel-Hakimi result. Okay. Havel-Hakimi result says that they will provide two sequences. They will provide two sequences. First, I'll write the theorem. Afterwards, I'll explain what is the importance of a Havel-Hakimi result. Suppose S T1 comma T2 comma T3 up to so on TS comma D1 D2 D3 up to so on DN to so on DN. Where it is second one T1 minus 1 T2 minus 1 T3 minus 1 and so on TS minus 1. Okay. The remaining part we can write as it is D1 D2 D3 up to so on DN. DN. So we have two sequences, provided the first sequence always in the descending order. First sequence always in the descending order. Okay, that point also can mention. Here, sequence one is in the descending order. In the descending order. So if this condition satisfies, now what is the meaning of Havel-Hakimi result? Equation one is graphic or graphical sequence. Graphic if and only if equation 2 is graphic. What does it mean? Suppose if equation 2 is a graphical sequence, then obviously equation 1 is also graphical sequence. Or if equation 1 is graphical sequence, then equation 2 also graphical sequence. Here, what is the meaning of first sequence? Please understand this S indicates that we have to consider first S degrees. First S degrees. Like here T1 is indicate degree, T2 also indicate degree, T3 also indicate degree, and TS also indicate degree. Means we have to consider S vertices degree. Okay, we have to consider S vertices degrees. From those S vertices degrees, we have to subtract one. We have to subtract one. Look at the second equation. From those S vertices degrees, we have to subtract one from each degree. Okay. Then we are getting second sequence. If the second sequence is graphic, then obviously first sequence also graphic. That is Havel-Hakimi result. Okay. Maybe if you see like this, you'll get confusion. Therefore, I'll take one beautiful example by using example I'll explain this problem. Okay. Just observe how exactly Havel-Hakimi result is working. Suppose we have taken one simple example here, which is a simple graph because there are no self loops, there are no parallel edges. It's a simple graph only. Okay. And I'm taking graph names like vertices like A, B, C, D, E, F, G. First, we list out degree sequence for the given graph. Degree sequence. So degree sequence always in the form of either increasing order or decreasing order, right? Here we can write in the descending order. Okay, decreasing order. So what is the degree of A? Degree of A is equals to 3. Degree of A equal to 3. And degree of B is equals to 2. Okay. Degree of C, 1, 2, 3, 4, 5. So which is 5. Degree of C equal to 5. And degree of E, which is equal to 2. Degree of F, 3. And degree of G, which is 2. And degree of D, which is 3 like this. Okay. If I write in the descending order, the degree sequence is looking like this. Starting from 5, 5. After 5, next one is 2 times 3. Sorry, 3 times 3. 1, 2, 3. 3. And afterwards, how many times 2? 3 times. 2 times. 3 times. Total we have 7 vertices. Therefore, I have taken 7 degree sequence. Okay. Now I'm going to discuss this important point with respect to Havel result. So what I will do, first I will remove this vertex 5. I will remove this vertex 5 along with all its edges. Just I'm removing this vertex 5 along with all its edges. As a result of removing that vertex along with all its edges, what will get now? Just remove that vertex along with all its edges. So this edge will gone. Okay, this edge also will be removed. 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 Then the modified diagram is looking like this. The modified diagram. Like A, B, D, then G, F, then E. What about C? C vertex is deleted along with all its edges. Now rest of the graph is G to F and then G to D, D to A to B. Of course, F to E also there. Okay, F to E also there. Okay. Remaining edges like CF, CD, CA, CB. 1, 2, 3, 4, 5 edges removed. So clearly we removed 5 edges. Is it clear? We removed 5 edges. After removing, what is the degree sequence for this one? What is the degree sequence for this one? Let me draw the degree sequence for this. Degree of A is equals to 2. Degree of B, which is pendant vertex, that is 1. Degree of D, which is equals to 2. Degree of G, also 2. Degree of F, which is 2. Degree of E, only 1. Only 1. Just write in the descending order. Descending order, what we'll get? We'll get 2, 2, 2. Okay, how many times 2? 1, 2, 3, 4. 4 times 2. Right? 4 times 2. Afterwards, 2 times 1. 2 times 1. Right? Earlier, how many times 2 we have? G is equals to 2 and A equal to 3, D also 3. Let me write this one is the degree of C. Assume that is the degree of D, it is the degree of A, and it is degree of F. Degree of F. Okay. Rest of them are like G, G, and then E, B. These are remaining vertices. They are degrees. Right. See what we got. This is a degree sequence for the given graph. The degree sequence for the given graph. Now what I will do, again I want to remove one more vertex. I want to remove one more vertex. Slowly I'm giving motivation towards the Havel result. Afterwards, I'll explain how exactly Havel result is working. Just assume that I want to remove one more vertex. Assume that this time I want to remove vertex A. I want to remove vertex A. Okay. So imagine it is a degree of A, degree of B like this. Suppose this time I want to remove vertex A. If I remove this vertex A along with all its edges, what are the remaining vertices we are having? We have D, and then G, F, and then E. Okay. So here D to G we have H, G to F also we have H, the F to E also we have H. Okay. F to E also H. So we have only one vertex here, that is B. B. Here we have one vertex, that is B. So which vertex removed here? We remove A. Remove A here. Now if I see the degree sequence for this vertex, so E is having degree 1, F is having degree 2, G is having degree 2, D is having degree 1, right? And B is having degree 0. Degree 0. Because this is isolated vertex, right? That's a degree 0. Therefore, if I write in the descending order, their degrees like 2, 2, 2, 1, 1, 0 like this. 2 to 1, 0. Okay. So this is the degree sequence. Now I'm going to discuss Havel result by using these examples. Okay. Just observe this example. Look at the first statement. S comma T1 comma T2 T3 up to some TS D1 D2 D3 DN. This is the given degree sequence for the graph. Okay, the given degree sequence for the graph. For example, if I consider this example, this example having degree sequence is this is a degree sequence. I'll write the degree sequence now. 5, 3, 3, 3, 2, 2, 2. This is a given degree sequence. Okay, it is the first step. Please understand first step. Okay, this S indicates that we have to consider first S vertices degrees. First S vertices degrees. Here, who is S in the place of S? Who is sitting here? Obviously, that is 5. 5. So we have to consider first 5 vertices degrees. First 5 vertices degrees. What are first 5 vertices degrees? This one, like this. First 5 vertices degrees. Okay. After considering from those vertices, what we have to do? See here, T1 minus 1, T2 minus 1, T3 minus 1, up to so on TS minus 1. Rest of the vertices are as it is only. Rest of the vertices degrees are have written as it is only. Right? Therefore, from 3 we can subtract 1. 3 minus 1, that is 2. Again 3 minus 1, which is 2. 3 minus 1, which is 2. And 2 minus 1, which is 1. 2 minus 1, that is 1. Remaining we can write as it is, that is 2 only. Okay. After writing this, now arrange them in the decreasing order, because this is not in the decreasing order, right? If I arrange them in the order, which is decreasing order or descending order, arrange the descending order. If I arrange the descending order, I will get 2, 2, 2, like 2, 1, 1, like this. 2, 1, 1, which is same as this one, correct? Which is same as this one. Which is same as this one. Now, Havel result says that if it is a graph, if it is a graphic, means if it is a simple graph, then obviously given degree sequence also represents simple graph. Clear? That is the meaning of the statement. If this total degree sequence forms a simple graph, then the given degree sequence also forms simple graph. Okay. Suppose if you are unable to decide whether it is forming simple graph or not, if you are unable to decide whether it is forming simple graph or not, then we can repeat the same process. Observe how I'm going to repeat the same process now. Now this is a sequence we got, right? Okay, which is in the descending order. Now again repeat the same sequence now. Okay, this is first step over. First step over. But still we are unable to understand whether it is forming simple graph or not. Then I can take the sequence again. That is 2, 2, 2, again 2, 1, 1. What does that Havel result says that? Havel result says that first just point out first degree. So that is indicate S. That indicate S. Okay, here what is the first one? 2. Place a dot here. Okay. So now you can consider next immediate two vertices degrees. From those two vertices degrees, you have to subtract one. Okay, means you have to consider only this part. Okay, from that you have to subtract one. Now 2 minus 1 that equals to 1. 2 minus 1 that equals to 1. Remaining we can write as it is. That is 2, 1, 1 like this. That is actual meaning of Havel Hakimi result. See here. If I take S from first S vertices degrees, we have to subtract 1, 1, 1, 1. Remaining we have written as it is, right? Okay. Here also I did the same thing. What is the first value here? 2. 2 means you have to consider next immediate two vertices degrees. From those you have to subtract 1. 2 minus 1, 1. 2 minus 1, 1. Remaining we can take 2, 1, 1 as it is. Okay? But tell me, is it in the descending order? No, it is not in the descending order. Therefore, we can arrange them in the descending order. Descending order. Okay. By arranging them in the descending order, we'll have 2, 1, 1, 1, 1 like this. 2, 1, 1, 1. Okay. By arranging the descending order, we'll have 2, 1, 1, 1. Right? Now suppose if it is forming a graph, if it is forming a simple graph, then automatically, if it is forming a simple graph, then automatically I can say previous one is simple graph. If it is simple graph, then I can say previous one is simple graph. This is called Havel-Hakimi result. Let me verify, is it possible to draw the graph of five vertices. Out of five vertices, four vertices having degree 1 and one vertex having degree 2. Okay, one vertex having degree 2. Is it possible or not? Let me check it. Okay. If you are unable to decide whether it is forming or not, then you can continue this process. You can continue this process. Okay, but it's enough we can verify here itself, right? It's enough we can verify here itself. Suppose I can take five vertices. Okay, five vertices, and there is only one vertex of degree 2. I can take, there is only one vertex of degree 2, and this vertex having degree 1, this vertex also having degree 1. I can also draw like this, right? It is a simple graph. Since it is a simple graph, therefore the previous one degree sequence is simple graph. If it is simple graph, previous one also simple graph. Okay, so this is the way we can represent Havel-Hakimi result. Clear? So let me explain once again the theorem. The theorem says that first you consider the sequence. First consider the sequence. Now identify the first one. First one is here S. It indicates that next S vertices degrees, from the next S vertices degrees, you have to subtract 1, 1, 1, 1, 1, 1, 1, and verify that result is in the descending order or not. If it is not in the descending order, arrange in the descending order. Arrange in the descending order. If it is a descending order, then verify if it is simple graph, then the given sequence also simple graph. So equation 1 is graphic if and only if equation 2 is graphic. Remember, equation sequence 1 always in the descending order. Okay. If sequence 1 is not in the descending order, we have to convert in the descending order. Okay. For example, here I have taken this example. This 5 indicates that from the next immediate 5 vertices degrees, you have to subtract 1. Therefore, I subtracted 1, 1, 1 like this. Okay. 1, 1, 1. Okay. 1. And finally, we got this result. But I don't know whether the sequence is forming simple graph or not. Then what I have to do? I have to repeat the same process, right? For that purpose, I have to arrange again the descending order. Arrange the descending orders. Okay. Then in the descending order, the first one indicates 2 here. So it means that from the next immediate 2 degree vertices, you have to subtract 1. So by cutting this one, 2 minus 1, 1, 2 minus 1, 1. Remaining, we don't want to change them. We can write as it is. Now again arrange in the descending order, like 2, 1, 1, 1 like this. Okay. If it is a simple graph, then the given sequence also simple graph. It means that the given sequence is a simple graph. So clearly it is a simple graph, right? Okay. This is the way we can do the problems. Okay. Right? This is called Havel-Hakimi result concept. I hope you understood the Havel-Hakimi result. Okay. Let me solve one of the previous paper gate question. You can understand how exactly Havel-Hakimi result is working. Okay. This question is asking one of the gate paper. Which of the following is a graphical sequence? Which of the following is or are graphical sequence? Graphical sequence. So they provided four options. I can say they provide four statements. In the first statement, 7654, 7654, 4321. This is the first degree sequence. Second one, double three, double two. Third one, 7664, 43 double two. Fourth one, 877 64211. So I want to verify which of the following is forming graphical sequence. So since you are sitting in the exam hall, so you have to eliminate the options very quickly without wasting time. Okay. Can we eliminate some options first? Yes. Please recall the properties. Suppose in a simple graph, if there are n vertices, in a simple graph, if there are n vertices, every vertex can have at most degrees n minus 1 only. Every vertex can have degree at most n minus 1. It cannot have more than n minus 1. Okay. Now look at options here. There are total there are total 8 vertices. 8 vertices, at most 8 minus 1, 7. Yes, it is okay. Next one is also okay. Next one also okay. But if you see fourth one, there are 8 vertices. In 8 vertices simple graph, how can I get a vertex having degree h? In 8 vertices simple graph, how can I have a vertex having degree 8? Is it possible? No. So we can eliminate this option. Option 4 is eliminated. Okay. So by using first property, we eliminated option 4. Next, sum of degrees of all vertices must be even, right? But before verifying that, first verify how many number of odd vertices are there. Number of odd vertices must be even. Okay. Here it is odd vertex. Here also odd vertex. It is also odd vertex. Odd vertex. They are even. Okay. Here there are two odd vertices. They are also even. Here how many odd vertices? Two odd vertices. So by using that property, I cannot eliminate any option. Next property, sum of degrees of all vertices must be equal to even number. Okay. Just sum up all the values and verify whether they are providing even number or not. Okay. So 7 plus 6, 13, plus 5, 18, 22, 26, 29, 31, 32, which is even number. Okay. Sum of degrees of all vertices are even number. Here 24 plus 27, 30, 32, 34, which is also even number. Okay. Next, 13, 19, 23, 27, 30, 32, 34, which is also even number. So by using that property also I cannot eliminate. Okay. Can I apply plotting method? But here there are 8 vertices are there, right? If you have 8 vertices, applying plotting method will take more time. Therefore, my suggestion is you can directly apply Havel-Hakimi result. Remember, friends, when you're applying Havel-Hakimi result, you no need to consider all these properties. Just I want to refresh all these properties. Therefore, I explained by using properties. But the moment if you want to apply Havel-Hakimi result, you no need to go for all these properties. Directly you can apply Havel-Hakimi result. So after eliminating option 4, directly can apply Havel-Hakimi result. Now I'm going to discuss Havel-Hakimi result for the first problem. 7, 6, 5, 4, 4, 3, 2, 1. This is the given sequence one, the first sequence. But according to Havel-Hakimi result, in the first sequence, first number we have to identify. What is the first number? That is 7. 7. It indicates that from the next 7 consecutive degrees, you have to subtract 1. Okay. From the next 7 consecutive degrees, you have to subtract 1. So what are the next 7? Like all this. Correct or not? Okay, you have to subtract 1. So 6 minus 1, that equals to 5. 5 minus 1, 4. 4 minus 1, 3, 4 minus 1, 3, 3 minus 1, 2, 2 minus 1, 1, 1 minus 1, 0. Okay. Now tell me, is it graphic? Is it graphic? Means is it a simple graph? If suppose, if you know that it is simple graph, if you say it is simple graph, then the given sequence also simple graph. That is called Havel-Hakimi result. Okay. Suppose assume that you are unable to find whether it is simple graph or not. Then what we'll do? So you got it is first sequence. Now it is second sequence, right? Second sequence. I want to verify second sequence is a simple graph or not. I want to verify second sequence is a simple graph or not. Again, repeat the same process. Now, whenever you are going to verify second sequence, simple sequence or not, verify in the decreasing order or not. Yes, it is a decreasing order. Okay. Now let me consider this part is already over. Okay. Now I'm taking second sequence. 5, 4, 3, 3, 2, 1, 0. Very simple, friends. Okay. By using first sequence, you generated second sequence. See, by using first sequence, you generate second sequence. Now, if you can say second sequence is simple graph, obviously first sequence is simple graph. If you're unable to say second sequence is simple graph, again apply Havel-Hakimi result. Now it becomes first sequence now. First sequence. Verify the descending order? Yes. Just I have written the sequence here only. That's all. Okay. And what is Havel-Hakimi result now? The first value indicates that from the next 5 consecutive degrees, you have to next five consecutive vertices degrees, you have to subtract one. Okay. Then 4 minus 1, which is 3, 3 minus 1, 2, 3 minus 1, 2, 2 minus 1, that equal to 1, 1 minus 1, 0. You no need to subtract any value from 0, but keep 0 as it is. Now we got second sequence. Second sequence. Do you know that it is a simple graph? Suppose if you know that it is simple graph, then obviously I can say given graph is simple graph. Okay, obviously I can say given graph is simple graph. Suppose if you are unable to find whether it is simple graph or not, again repeat the same process. Okay. So this part is over. Now the previous second sequence you can consider the first sequence. Now the first sequence is 3, 2, 2, 1, 0, 0. Now identify first one. First one. It means that from the next three degrees, from the next three vertices degrees, you have to subtract one. So this is the next three vertices degrees. Like 2 minus 1, 1, 2 minus 1, 1, and 1 minus 1, that is 0. Remaining all are zeros. We can keep them as it is. Okay. This is second sequence. Now tell me, friends, can you say it's a simple graph? Can you say it's a simple graph with 5 vertices? Let me draw this graph now. I can easily say, right? I have 5 vertices. Okay, where one vertex degree is 1, another vertex degree is also 1. Like this. This is a given graph. A, B, C, D, E. Okay. Since this graph is simple, therefore its previous graph also simple. If it is simple, then its previous graph also simple. Okay. Then if it is simple, then the given graph also simple. This is the way we can trace out Havel-Hakimi result. Okay. Therefore, the first sequence is a simple graph sequence. So it is a first sequence is graphical sequence. Is it clear? The first sequence is a graphical sequence. Okay. First sequence is a graphical sequence. What about second sequence now? 4 times 6, 3, 3, 2, 2. Let me check second sequence. 4 times 6, 3, 3, 2, 2. I want to verify is it forming graphical sequence or not. Okay. We can call it the first sequence. From this first sequence, we want to generate second sequence in Havel-Hakimi result. How to generate? Identify first value. That first value indicate 6. Now consider next immediate 6 values. Next immediate 6 values. From those 6 values, you have to subtract 1. 6 minus 1, that is 5. 6 minus 1, 5. 6 minus 1, 5. 3 minus 1, 2. 3 minus 1, 2. 2 minus 1, 1. Remaining 2 we can write as it is. Okay. Now, if the second sequence is the simple graph, then obviously first sequence also simple graph. But can you identify second sequence is simple graph or not? Is it possible? If it is not possible, then repeatedly apply the same process. Let me go for next search. Now it is already descending order. Therefore, I can consider 5, 5, 5, 2, 2, Sorry for the mistake. It is not the descending order. We have to arrange the descending order. So 2, 2, 2, 1. Okay. Now it becomes first sequence. Please remember, after getting second sequence, the second sequence is not in the descending order. You have to arrange the descending order in order to apply Havel result further. Okay. Now identify first value, which is 5. It means that you have to consider next 5 values. Consider next 5 values. From those 5 values, you have to subtract 1. 5 minus 1, 4. 5 minus 1, 4. And 2 minus 1, 1. 2 minus 1, 1. And 2 minus 1, 1. Remaining 1 we can write as it is. Okay? Remaining 1 we can write as it is. Suppose if we say it is a graph, if we say it is simple graph, obviously previous one is also simple graph. Assume that you are unable to identify the simple graph or not. Okay? Then again, go to next one. Next one. Actually, it is not required to do like this. The reason is it is having degree 4 and it is also having degree 4. It means that this vertex is connected to 4 other vertices. And it is also, second one also connected to 4 other vertices. Then how it is possible to get 1, 1, 1, 1, 1 here? Is it possible? No, right? Are you getting my point? This vertex is connected to 4 other vertices. This vertex also connected to 4 other vertices. Then definitely we cannot have vertices, we cannot have 4 vertices of degree 1 like this. Okay? Therefore, it is not a valid simple graph. I hope you understood what did I say. Right? Since it is this vertex 4, this vertex whose degree is 4, adjacent to remaining 4 other vertices. Okay? This vertex also adjacent to remaining other 4 vertices. Then how can I get remaining 4 vertices are having degree 1? No, it is not possible. Therefore, it is not simple. It is not simple graph. So therefore, I can say second one is not simple graph. Okay. Now what about third one? Third one, which is equal to 7, 6, 6, 4, 4, 3, 2, 2. Okay. Can you quickly apply the Havel result? First value is 7, means from the next 7 values you have to subtract 1. From the next 7 values you have to subtract 1. Okay. So 6 minus 1, which is equal to 5. 6 minus 1, 5. 4 minus 1, 3. 4 minus 1, 3. 3 minus 1, 2. 2 minus 1, 1. 2 minus 1, 1. Okay. Verify in the descending order. Yes, they are in the descending order. Now it is our first sequence. It is second sequence. Here, if you know that second sequence is a simple graph, obviously first sequence also simple graph by using Havel result. Assume that we are unable to decide second sequence simple graph or not. Now again repeat the same process. Okay. I can take second sequence now. 5. I can take second sequence now. 5, 5, 3, 3, 2, 1, 1. Which is in the descending order. Now I can consider it as a first sequence. Okay. In the first sequence, first value is 5. Means from the next 5 values, you have to subtract 1. From the next 5 values. 5 minus 1, 4. 5 minus 3 minus 1, 2. 3 minus 1, 2. 2 minus 1, 1. And 1 minus 1, 0. And here it is 1. Okay. Now verify is in descending order. No, it is not a descending order. Now to apply further, you have to take in the descending order. Okay. Now it is second sequence here. Now the previous second sequence must be in the descending order. By in the descending order, 4, 2, 2, 1, 1, 0. We can consider the first sequence. Again, apply Havel result. So it is the first one whose degree is equals to whose value equal to 4. Means from the next 4 consecutive values, you have to subtract 1. 2 minus 1, 1. 2 minus 1, 1. 1 minus 1, 0. 1 minus 1, 0. And we have 0 like this. Okay. So there are 5 vertices. There are 5 vertices. And in that, 2 vertices having degree 1 and 3 vertices are having degree 0. Obviously, we already done this kind of example, right? I can draw graph like this. So 2 vertices are having degree 1 and remaining 3 vertices are having degree 0. Therefore, this example Third one is also forming simple graph. In the exam, they provide these statements. They're asking which are the following like are graphical sequence. They provide options like this. First option, only one, okay, and second option, only one and three, and two more options like this. Okay, then what is the correct answer for this one? Only one and three. So this is the way you have to analyze the problem, right? So in this video, we discussed how degree sequence is converted into simple graphical sequence by using Havel result. Okay. In the next video, I'm going to discuss basic definition about regular graph and then followed by cycle graph, wheel graph, complete bipartite graph, and then bipartite graph. I hope you are enjoying by watching these videos. Okay. So I'm going to discuss so many workload examples in graph theory. So minimum for each and every topic, minimum I'm going to discuss 15 to 20 questions so that you will be perfect in the topic. Okay. So thanks for watching this video.